Let's take a look at example 2.6 from our text. In this example here, they ask us to use the principle of virtual displacements to derive the equation of motion of the idealized single degree of freedom system as shown below in the figure. They tell us to neglect gravity and assume small angular rotation of the beam. Now if we look down below at this figure, we have a uniform beam with a distributed load. We can see this distributed load across the beam here. We have a relationship for this load right there. We can see that the total length of the beam, we have length here L. We can see we start at point A at a frictionless pin, move up to here at a point B, some distance A away from this frictionless pin. We can see here we have a spring constant K. This is a massless linear spring. Come all the way to the end of point C here. You can see now we have a damper down here at this point, at point C, at the end of the beam. So now that we've had the opportunity to read through the problem statement, take a look at that given diagram, and understand what they're asking us to solve for, the next thing we want to do is create our setup page. So on our setup page again, we want our given diagram, everything clearly labeled, anything else they give us within that problem statement. Down here we have a labeled section, so we know exactly what they want us to find. They want us to derive an equation of motion of the idealized single degree of system that we have shown up here above. And now in this problem here, we also are going to add our assumptions. They tell us two things in the problem statement that we can add to this section here. We want to neglect gravity and assume the small angle rotation of the beam. So we can go back up here. You can see I've kind of color-coded this a little bit, simplified a little bit. And again, this gives us a page to come back to as we're going through our solution to look at that diagram again, understand what they give us and what they're asking us to solve for. Now that we have our setup page completed, we can begin our solution. So our solution is going to have multiple steps. The first step in our solution here, we're going to do is sketch the body of an arbitrary displaced configuration and also with the virtual displacement as well. So what we want to do, come down here, we can redraw this out, simplified version here. We can see we have our total length L, we have this distance x. Up until right here we have our v there. Then we have our delta v as we go up here. A dotted line there. Theta, delta theta there. V of x comma t is equal to x times the tangent of theta of t. Now, for a small theta down here, we have these relationships here. For a small theta, instead of this relationship here, we can do this based off our assumption that v of x comma t is equal to x times theta of t, and delta v of x comma t is equal to x delta theta. So this again is for that assumption for a small theta. For the next step of our solution, what we want to do is create a sketch of the body, and on this sketch we want to show all of the forces that can do work, including our inertia forces there. First thing I've done is established a given coordinate system here. I choose x positive right, y positive up, helping my sign convention here. I come down, draw out my diagram here. So we have this here. We can see, okay, at this point A, if we go back, this was our frictionless pin. If we go back to the very beginning over there, then we also had a spring force acting here at point B, and at the very end over here, we had a damping force over here, and then we have our distributed load as well. The other thing that we have is our inertial forces here, so here's our F sub I right there, and our moment as well. So we put all those on there. At the same time, what I want to do is draw out all my distances from a reference point, and we consider the reference point to be that frictionless pin. Back here, we're going to call point A over here. So we look at here, okay, if I go up to my spring force here, F of S, that's a distance A away. I go up to where my F sub I is for my inertial force here, that is a distance of L over 2 halfway across. Then if I go up here, now my F sub P over here, this is at 2/3 L. And we go over here to my damping force F sub D, that's at a total length of this at L. So now I have the second part of this done. I have the diagram drawn out. I have my forces drawn on this that can do work. I have my sign convention here because I know anything going up is positive, anything going to the right is positive, anything down is negative, anything to the left is negative. So my next step in the solution here is to write out the virtual work equation. My delta W is equal to 0. So what are the things that do work? Well, that's why I drew out this diagram. So now I know all my forces that can do work, including the inertial forces, so then I can plug that in to this equation down here. So if I move this up just a little bit here, we can see this equation here as we plug in. So start, look at all these. Okay, I have my f of s. We can say my f of s is negative based off of my chosen coordinate system here, times this distant a here, times my d theta. Again, that's based off of that assumption. We got rid of the tangent there because we're doing small thetas. Same thing on the f sub d. If I look here, my f sub d is going to be down in the negative direction there. So I have negative f sub d times this total length over here of L times d theta there, plus my f of p force here times my 2/3 L right there times d theta right there. Then I have my inertial force right there at L over 2 halfway up this times my d theta there. And then I have my moment right here times d theta. This is equal to 0 when I plug those all in to this virtual work equation. For the next step in our solution, what we want to do, step 4 here, is to relate the forces to motion variables. We'll start out with a spring here. We call f of s equals ks. For our problem here, we now have f of s is equal to k times a distance there from our frictionless pin up into where our spring is located, times theta. F sub d, the total length of the spring there, L. F of d is normally equal to cv. For our case here, f of d is equal to cl times our theta dot. So we also again have this now. We relate their forces here, our f of p force, our f of I, inertial force, and our moment there. F of p is equal to p naught times L over 2 times f of t. F of I is equal to ml over 2 times theta double dot. And for our moment here, for a general moment equation for a beam here, we have ml squared over 12 times our theta double dot. So go back through the chapter and through the lecture notes. If you're not sure exactly how we came up with these guys here, we can review that. Most of these are from previous courses as well. So this brings us now to our last step in our solution, step number 5 here. In this part of the problem, what we're going to do is combine our previous equations. Delta W, Fs, Fd, Fp, Fi, and Mi. We now have relationships for all of these. We can plug those in to our previous equation that we solved for there. So when we do that, we have our delta W is equal to 0. So we can plug our 0 into this side here. Our f of s we found to be k, a, theta. We plug that in for our f of s there. Our f of d we can replace with cl theta dot. Our f of p we can replace with p naught L over 2 times f of t. Our f of I is ml over 2 times theta double dot. And our m sub I is ml squared over 12 times theta double dot. So now we can plug all those into where we've circled in green here for each of those forces. Moment, plug that in, we end up with this relationship down here. So take a look at this, plug that in. Now we have 0 is equal to k a theta times a delta theta minus cl theta dot times L delta theta plus p naught L over 2 times f of t times L delta theta times 2/3 minus ml over 2 times theta double dot times L over 2 d theta minus ml squared over 12 theta double dot d theta. Now the thing that we can note here as we're looking at this, we want to reduce and simplify it. We can pull out delta theta out of this whole thing. So we do that. We pull our delta theta out front here. Delta theta times our ka squared theta minus, now we have here cl squared theta dot. I'm going to pull this out front as well. Plus 2/3 of p naught over 2 times L squared f of t minus ml squared over 4 theta double dot minus ml squared over 12 theta double dot. So look at here, okay, these are similar. We can combine these two together, put this over 12. We have here 3 over 12, 1 over 12 there. We end up with negative 4 over 12 there. Negative 4 over 12 is a 3. So then we can come over here and rearrange and simplify a little bit more once we combine those together and do a couple more simplifications. This now becomes our ml squared over 3 times theta double dot plus cl squared theta dot plus ka squared theta minus our p naught L squared over 3 f of t times now this delta theta. This is equal to 0. Well, our delta theta cannot be equal to 0. Therefore, we can take the left-hand side, let's set the left-hand side equal to 0 here, eliminating the delta theta out of that. So we end up at ml squared over 3 times theta double dot plus cl squared theta dot plus ka squared theta minus pl squared over 3 times f of t is equal to 0 now. Rearrange this slightly, move this over to the other side here. We come up with our final answer of ml squared over 3 times theta double dot plus cl squared theta dot plus ka squared theta is equal to our p naught l squared over 3 f